In Chapter 2, we're going to discuss architecture styles in distributed systems. In architecture, style is formulated according to, first of all, the components. So each component has well-defined interfaces towards the other components. Another important criteria is the connection between these components, and also the data that's being exchanged over these connections from one component to the other, and overall how we define all the interaction between the components and the connectors between these components, so that altogether we have a jointly configured overall system. So what's a component? A component is simply any mechanism that defines how communication and coordination is performed between the components in a distributed system. So, for example, you could be interacting from this component to another one using remote procedure calls, RPC, or you could be using a messaging system, sending messages through a message box, or you could also open a stream and just stream the data in a continuous manner from one component to the other. We could have three different ways of defining the layers when we are talking about a layered architecture. So in a layered architecture, the simplest one will be what we see in part A over here. So we have several layers. Typically we'll enumerate the lowest layer, layer 1, and all the way up to layer n. So this, as you will remember, immediately directly corresponds to the layered architecture in the OSI reference model, like the network reference model of ISO. As you know, for example, we have the physical layer, data link layer, network layer, transport layer, session presentation and application layers in the OSI reference model. So that one is just going according to the definition in part A. So in this simple basic layered approach, each layer provides a service to the upper layer. So for example, layer 1 provides a service to the layer 2. For example, in the case of OSI model, the physical layer provides a bit stream to layer 2, where layer 2 does the framing and it provides the packets, for example, to layer 3 by managing all the tasks that should be done at the link layer from one end device to the other in a single hop. And then the network layer provides the segments to the transport layer, for example, TCP or UDP segments, whatever, it works this way. So the lower layers provide service to upper layer, or you can look at it the other way around. The upper layer gets a service from the lower layer. However, when it is communicating according to this layered architecture to a different machine at a distance, each layer appears to be running a peer-to-peer protocol. So for example, layer n on device A communicates with layer n again in device B. n-1 communicates with n-1, n-2 communicates with n-2. So the protocol in between is called peer protocols, because these are this is a protocol between two peer entities at the same layer. In reality, those layers, of course, cannot talk directly to each other. In fact, they get the services from their lower layers. So this is what you know typically from your computer networks course. The different approach in part B is somewhat closer to what we have already discussed in part A, but the difference is that in some layers it is possible to go either from layer n-1 to n-2 and from n-2 to n-3, so following this path as I show on the screen, or It could also be possible to go directly from layer n-1 to n-3 by skipping n-2. Examples of this could be as follows. For example, layer n-3 could be providing the operating system services like system calls. So an application could directly make use of the system calls. But instead, it is also possible for the application to go through a system library like printf, scanf, or math functions, or any other kind of library, which actually makes use of the operating system calls over here. So the library here provides utility functions to layer n-1, the application, for example, so that the application does not have to deal with the intricacies of making system calls. But if the application wants to do so, still it's welcome to bypass those system libraries. So that's an example of this mixed approach. Rarely we have the third approach, where this is actually, as you can see, very similar to part A, but the difference is that this time the lower layer is also able to create an upcall. That means initiate a connection or a service request from the lower layer to the upper layer. Example of this could be like layer n-2 could be initiating an upcall when a specific event occurs. For example, you already have an ongoing connection, but what if the connection is broken? If the connection is broken from the distance side, you will be receiving an ICMP package saying the connection has failed. So you might need to inform the upper layer about this event, and this is not an expected event. So we cannot wait for layer n-1 to ask layer n-2 if there's something wrong all the time. So instead, only when that infrequent event happens, you create an upcall bottom up. So that would be the third approach in the case of layered architecture. So this is actually explaining what I discussed in part A in the previous slide. So we have several layers. Each layer is getting a service from the lower layer. However, conceptually, looks like layer n is talking to layer n-1 is talking to layer n-1 through some of these dotted line peer-to-peer protocols. Now, the way layer n-1 provides a service to layer n is through some interface. Okay, so this interface is actually the API. The API is simply actually your function signatures. So layer n-1 tells layer n that it has say function f1, f2, and f3, and f1 returns an integer, takes an integer parameter followed by a float parameter, whereas function f2 has some different parameters, and also the return value, of course, could be different, whatever. So these function actually definitions, but not the function body itself, just the signature, defines the API. So the API actually serves as an interface, and as you know, in the case of API, the letter I there stands for the interface. It's the application programmer's interface. So the interface is just defining what kind of functionalities or services layer n-1 is providing to layer n. But layer n is actually communicating with its counterpart, layer n-1. So altogether, this is called the service. It's an end-to-end connection. So as an example of this, here we have a very simple code for a TCP/IP connection, a socket connection. So you import the socket library or socket module. You open a socket, defining it as, for example, a TCP connection. You could do the similar things with UDP. So let's say our socket is named S. Then when you call s.accept, it will start waiting for connections from clients. So the service is the server process actually at this point states that it's now attached to this specific port at this IP and ready for accepting connections from remote clients. And we go in a loop waiting for connections. The server process typically will go to sleep until a connection arrives. When a connection request arrives, it will wake up. It will receive the data. If there's a problem with the data, it might stop. Or you may take another action, of course. And if not, if everything is fine, it will prepare the response and then send the response back. In this case, for example, we are just bouncing back the message we had received by just appending an asterisk at the end. So this is how the server would connect. On the other side, the client also needs to create a socket, but the socket created by the client will not wait for incoming connections because it's the client, not the server, but instead it will go to the host IP of the server and at that specific port number, because remember that at one server you could have many services running, so you have to specify which service you want. Then you send your data and typically receive a response and do whatever processing you want. In this example, we're just printing it on the screen, but of course you can do anything. And when you're done, we don't want the connections to stay alive even if we're not using it. So we typically close the connection. Note that this is a very simple client-server design. In this case, for example, the server is capable of responding to a single client at any time. Therefore, if the client does not close the connection, it would remain up at the server side. So even if you're not doing anything, even if you're not communicating with the server, you would also be preventing other clients from connecting. That's why you have to specifically close it. In the case of more advanced server designs, we typically fork the server so that the duplicate, the child process, can serve the incoming request from that client while the server keeps on waiting at that well-known port number for new incoming requests, so that you could serve multiple clients simultaneously. Looking at the layered approach, the layered architecture, it is also possible to look at it from a different perspective. So we can say we have an application interface layer which contains the units for these interfaces to either users or to other applications or other machines. The second one would be the processing layer. This is actually what your business logic is. So your business logic is implemented here. What I mean by business logic is whatever you want to do in that project. The real processing would be over here. And of course, your process is working on some data. So there is also the data layer, which retrieves the data typically from a disk or from a database. And you process it, and possibly you're also trying to write it back. So all that physical data communications would be at the data layer. The logic would be at the processing layer, and the interfaces will be made use of using the application layer. So this way we actually split the overall task into three different layers or approaches. This layering is found in many distributed information systems, making use of typical database technologies at the data layer, and as I said, interfacing the other applications or the users at the application layer, and whatever the process the project is doing at the processing layer. So here we have an example of that. This is the very rough schema of, for example, a search engine like Google, Yandex, whatever, is doing. So one thing is interfacing the users. What we mean is, for example, if you're talking about Google's search engine, then this is actually the web page you see when you go to www.google.com. So this is a simple, we try to keep it as simple as possible because of the load. This is a simple HTML page where you have a text box where the user can enter their search query and press the search button. And later this will also be used to display the results. But let's first focus on the entry side. So the user provides the search query. Note that the user it does not necessarily have to be a human being. For example, you could also provide an API to other applications so that applications on other computers could also make use of Google search without the user actually going to that web page. So that's why this is the application layer dealing with either users or other applications. Now we will get the query from here, and we will first analyze the query. For example, if it's something is in double quotes, you say it should be used as it is. Otherwise, you would just connect the words with and. If there's something like an or keyword there, then you're going to arrange the query according to that. If there's a filter, like you say site colon and then some website, it will be doing the search only under that website. Whatever, all these processing are done by the query generator to create a database query. So so Google has its own specifications for how you write your query, but finally it will convert to whatever its database supports into a database query. So this will be done at the processing level, because in this example, the process is actually finding the pages, and that requires preparing the correct query, database query. So that database query will be given to the database. Of course, in the case of Google, that's a huge farm of database servers. It's not a single database server. But for our case, we could just consider that to be a single system, okay, although it is a database farm, because we don't care about how many database servers there are, which one we should communicate with, whatever. We'll just send it to the database system, and that will do the parallelization there. Anyways, after this, the database system will prepare a list of links to different web pages, which is actually the result, with some meta information, and that will be given to the processing level, where the ranking algorithm now takes that list of links and then sorts them according to importance or other criteria, and these will be finally, this list will be finally converted to an HTML page, and that will be served to the user. So this is the concept of splitting the overall task into 3 different levels. Another approach is the object-based style. Well, as you can guess from the name, it employs the ideas of object-oriented programming actually. So now we have objects as the components, and these objects are, remember, the components are connected through connectors. So now the connectors are actually the procedure calls or method calls provided by each object to the other objects. And these objects can now be placed on different machines. They don't all have to be on the same machine, just to distribute the load. And the calls, therefore, are now not to local objects, but to remote objects. That means they have to pass through the network. So basically, it's like, as we have done always with object-oriented programming languages, we have a set of objects which provide interfaces to each other through these method definitions. So each each object is calling either its own method or the method of another object. So from our point of view, if you just try to generalize it, each object has multiple methods and a state. And remember, actually, this is what we were discussing even in the freshman years for object-oriented programming. The methods actually provide the actions, and the state is actually the set of properties or variables of that object. So this way, the object provides encapsulation of the data. That means for each object, actually, there are data items that are in different places. But the object definition hides this variation and provides only methods to the other objects through its object interface. So to the other objects, it appears like everything is properly wrapped or encapsulated into a single package as that object. Where the individual data items are stored, how they are accessed, what should be the interaction between these data items to provide the overall integrity of the object and integrity of the data, in other words. That's all left to that object. The object will take care of it. So we don't need to deal with the details, which makes the design, of course, simpler, especially in the case of large and complex systems. Yet another, by the way, sorry, before I pass to the next slide, this also opens up the way for the service-oriented architecture, the SOA architecture. How about the RESTful architectures? In this case, we view a distributed system as a collection of resources which are individually managed by the components, and we're able to add new resources, remove them, delete them, get resources, make modifications on the resources through these applications, whatever. So in the RESTful architectures, you should be providing for features. First of all, the resources are identified through a single naming scheme, and all services offer the same interface, which makes life quite easy. Messages sent to or received from a service are fully self-described, and after executing an operation at a service, that component actually forgets everything about the caller. In other words, this is called the stateless feature. So we're not keeping a state in that case on the resource side. So each resource should be providing these 4 operations, not more. These are put, which is for creating a new resource, get for getting or retrieving the state of the resource, delete to remove the resource, and post to modify the resource so that the state changes when you do the modification. For example, we can look at the Amazon's S3 systems. S3 system stands for, the S3 there stands for Simple Storage Service. So in Amazon's simple S3 system, there are two things: objects and buckets. The objects are typically, for example, the files, and the buckets are the directories. Note that you're not allowed to put a bucket in a bucket. So this is a very flat directory design, as you can guess. And considering that we want to deal with an object named object name in some specific bucket, let's call it the bucket name, then the way you access it is actually very well defined. You access it through HTTP queries. So you prepare an HTTP URI, in fact, and that would be the bucket name, like a directory, in s3.amazonaws.com, and after slash you specify the object name, which is typically the file. So all these are done through HTTP requests. So to create a bucket object, you say put and then this URI. To get the listing, you say get then this URI without the object name. Or to read an object, then you give the whole URI after get. So it's really simple, only 4 comments. You do everything with these 4 comments. However, Amazon also provides the SOAP architecture also, service-oriented architecture. So in the case of the SOAP interface, you have many, if I'm not wrong, it should be around 9 different operations. So operations like list all my buckets, create bucket, delete bucket, list bucket, get bucket access control policy and set it, and also get bucket logging status and again set it. These are for the buckets, and these are for the objects. So let's assume that we're talking about an interface for some bucket that provides the create operation, and we want to get an input string such as my bucket to create this bucket. So all you're going to say is first import the bucket module and then say bucket.create my bucket. This way you're going to create a new bucket in SOAP. In the case of RESTful, you would achieve the same task in a different way. This time, actually what you're trying to do, and also the variables to the get put commands would be through the URI. Okay, so you just say put where and what. That's specified inside the URI. So the URI actually contains the bucket. In the case of a get, you would also have the object name over here. Okay. Well, which one is better or worse? In some cases, or of course, again, some people are inclined towards the SOAP architecture, whereas others support the RESTful architecture. If we compare them, actually we can see that typically one is better in some sense and the other is better in another sense. So we cannot say easily there's a clear winner. But the general rule of thumb we can say is the RESTful interface has only 4 commands. So it appears to be simple, but in the case of complex projects, doing everything using those 4 commands might become a little bit more difficult. So SOAP is better in that sense for complex projects, but for simple projects, really RESTful approach is far better. On the other hand, in the case of RESTful interface, if there are any problems in your code, for example, you just make a typo while writing it, you will realize this only at the time of execution. Whereas in the case of SOAP interface, typically the compiler will be detecting, not of course all, but most of the errors at compile time. So in other words, RESTful interface requires a more detailed and more thorough debugging to see that you didn't make any mistakes. How about coordination? Now, we can define coordination in two different dimensions. One is a temporal coupling, that means coupling according to the time, whereas the other is a referential coupling, that means the requirements of referring to the exact components. Let me explain it in more detail. When we're talking about temporal coupling, we mean, okay, component A is trying to communicate with component B. If component B is not up and available, component A cannot proceed because they have to be up and available at the same time. So this is a temporal coupling. If A does not require B to be available at the moment A is sending the message, then they're temporally decoupled. Otherwise, they should be coupled if it requires that it's up and ready at that moment. How about the referential coupling? In the case of referential coupling, A wants to send a message, and it has to know that message has to be sent specifically to B, but not C. In the case of referential decoupling, A says, I want the service. I don't care if it's B or C or D or someone else doing it for me. All I want is, I want this thing to be done. It doesn't matter which one does the service. And also, I don't need to know those details. I don't need to know the names of the corresponding components, how many of them are there, which ones are available and which are not. It doesn't care about that. So if the two components in communication need to be up and running at the same time, and also they need to know, especially the source needs to know, source specifies who the receiver will be. That means it's referring directly to B, in other words. That's called a direct coordination. Now, consider that A wants to communicate with B, but it doesn't require that B is available at the moment. So if A will just send the message, and when B becomes available, it will receive the message, analyze it, and do whatever A wants, and then possibly send a message back to A as a response. And again, for the response, B does not require that A is immediately available. A might get the response when it is available and take care of it. In that case, they're still referentially coupled because A wants to communicate to B, B wants to communicate to A. However, they don't need to be available exactly at the same time. So that's typically a mailbox approach. So A writes its request to a mailbox, B reads from the mailbox when it's available and sends the response back to the mailbox of A. In the case of referentially decoupled and temporally coupled case, this time it's like an event has occurred and the event needs to be handled immediately, but I don't know who the receiver of that event should be. So you just raise, for example, just like raising an interrupt, you just raise an event handler. So you just specify that this thing needs to be handled, such an event has occurred, and it is immediately handled, but we don't know who's dealing with it. So you just say that such an event has happened. Whoever has been earlier defined to be handling that request would be the corresponding component, but we didn't specify it, so it's referentially decoupled. And finally, if you consider the case where, again, we don't care who handles it, and also it doesn't have to be done immediately at that moment, that would be the temporal decoupled and referential decoupled case, where the request is actually written into some shared data space until it is handled, and also we don't care who handles it. So the request is written to a shared data space until, in quotes, somebody, I don't care who, somebody handles it. Of course, it should be handled correctly. So when I say I don't know who, it should be a correct component doing it. But we don't care which component does that. So if we compare these two referentially decoupled cases according to whether it is temporally coupled or temporally decoupled, they are quite similar. So we have components that are actually making requests, and also the components that are providing services. So for example, here the component first subscribes on the event bus to a specific event, okay, and it will just be subscribed and remain subscribed that way. Whenever the event occurs, say on this component, it will publish the event to the event bus, and this event will be delivered to one of the components that was actually subscribed. So both of these components were subscribed earlier. It was, for some reason, delivered to this one, not the other. Whereas in the case of shared or persistent data space, it's persistent because the data remains there until it's retrieved. The component publishes the request, and it goes to the data space. It's written to the data space. At some point, not exactly at the same time, later on at some point, another component subscribes to that specific data item, and if it's already has been earlier published, it will get that data. If not, it will remain subscribed, and when this component publishes it, it will be informed about the data. So that's the basic difference. So a way to implement this is the Lynda language. So this is just an example. So in Lynda, we're talking about tuples. Also, actually, over here in the previous one, we also were mentioning the data as in tuples. A tuple is just like a single row in a database. So you have different columns. So those columns actually correspond to the values in the tuple. So we have three simple operations: in, RD, and out. So in the case of in with the parameter t, so you remove a tuple matching some specific template. With RD, you obtain the tuple, and with out, you add a tuple to the tuple space. Now, if you call out t twice in a row, then that will actually store two separate copies of the tuple. So a tuple space, therefore, could be a multiset. You could have multiple tuples for the same thing. Sorry. Both in and RD, these are blocking operations. So if you call in or RD operations, the caller will be blocked until in the database you find a tuple that corresponds to this. If not, then typically you will be blocked until one becomes available. So in other words, until someone writes such a tuple. So here's an example. We have two users, Bob and Alice, that are writing into a microblog, and another user, let's say Chuck, who wants to read it. Okay, so Let's first look at what Bob is doing. So first, Bob associates itself with a specific microblog. Let's call the microblog also with the name microblog. So it will get attached to this. And then Bob creates, now this is a very simple microblog. So we have the person who creates an entry. So that person is posting a message, in other words. So we will call a person who is posting a message as a poster. So the poster name is Bob. The title of the post is Distributed Systems. And the content of the message is I'm studying chapter 2. Bob then adds another entry, another message to the same, under the same title. But this time the content is the Linda examples, pretty simple. And finally, Bob also adds yet another message, a third message, but this time under a different title as Cool Book. Let's say Alice does a similar thing, so into the same microblog, Alice inserts 2 messages. One goes into the, under the same title, under the second title, Bob has used with this message. And the other is under the first title Bob has used with this message. Okay. Now, let's say the third user, Chuck, wants to read this. So first, Chuck will also attach to the same microblog. And then, for example, Chuck could read the message from Bob under Distributed Systems title, or from Alice under GTCN title, or a message again from Bob under GTCN title, whatever. As you can see, actually, things have been quite simple. Neither Chuck nor Bob and Alice need to do much to do this message exchange, and more important, they don't have to be temporally synchronized. So when Bob was entering these messages, probably Chuck was not even in the system. So that will be the end of this section.